Temperature is the single most influential environmental variable governing the operational efficiency and service life of stationary battery installations. This technical briefing compares lead-acid, nickel-cadmium, and lithium-ion chemistries, then translates thermal behavior into practical enclosure, cooling, charging, monitoring, and siting decisions for stationary duty. Stationary batteries rarely remain at the 25 degrees Celsius reference temperature used for rating. Low temperature slows ionic mobility and reaction kinetics, increasing internal resistance and reducing available capacity. High temperature can briefly improve apparent capacity and charge acceptance, but it accelerates side reactions, self-discharge, corrosion, electrolyte degradation, and permanent capacity fade. Battery aging follows an Arrhenius-type relationship. For lead-acid systems, the rate of damaging side reactions roughly doubles for every 8 to 10 degrees Celsius rise above 25 degrees. The article illustrates the consequence with a 10-year VRLA battery. Sustained operation near 33 degrees may reduce life to about 5 years, while 40 to 42 degrees may reduce useful service to roughly 1 to 2.5 years. Lead-acid is the most temperature-sensitive chemistry in this comparison. VRLA types are especially vulnerable because lost electrolyte cannot be replenished. Flooded lead-acid tolerates heat somewhat better, but requires ventilation and maintenance. Nickel-cadmium offers the broadest native thermal tolerance and long service in harsh stationary duty, although cost and cadmium regulation are constraints. Lithium-ion delivers strong energy density and cycle life, but requires a battery management system and deliberate thermal management. For lithium-ion systems, both average temperature and temperature uniformity across the rack matter. Uneven cooling causes uneven state of charge and uneven aging. The article cites a thermal runaway onset of roughly 270 degrees Celsius for lithium iron phosphate, or LFP, compared with roughly 210 degrees for nickel manganese cobalt, or NMC. This higher margin is a key reason hot climate utility systems commonly favor LFP. Thermal mitigation begins with siting and enclosure design. Reduce direct solar gain, use light-colored cladding, insulate battery-bearing walls, and avoid ground-level heat soak. Forced air cooling is established and effective, but adds parasitic load and maintenance. Liquid cooling can provide tighter cell-to-cell uniformity for high-density lithium-ion containers. Lead-acid chargers should use temperature compensation, while lithium-ion systems require battery management cutouts and current limits outside the safe temperature band. Gulf Solar Plus storage projects can experience summer ambient temperatures above 50 degrees Celsius. A shaded underpanel or open rack arrangement reduces direct solar loading, but it does not reject high ambient heat or the battery's own internal heat during charging and discharging. For small systems, passive shading may be acceptable with generous derating. For utility-scale lithium-ion, the article explains why shading alone is not an adequate thermal management strategy. Purpose-built containerized battery energy storage systems isolate the battery environment from solar and wind exposure. Dedicated air or liquid cooling controls ambient and self-heating loads, while insulation and ingress protection support desert operation. The standardized container format also improves cell temperature uniformity, commissioning, and replacement logistics. In the article's engineering comparison, an actively cooled LFP container is the regional utility-scale default, while a passive open rack is not. The central lesson is straightforward. Temperature affects immediate efficiency and capacity, and it also drives cumulative, largely irreversible aging. Select chemistry using the real site environment, not only nameplate conditions. Apply standards-based temperature correction and realistic replacement assumptions. Design the enclosure, cooling, charging, and monitoring system as one integrated thermal strategy. In hot climates, active thermal management is not an accessory. It is a primary reliability and life cycle design function.